Okay. All right. So let's hope this works. So we are going to be talking about sets and configurations again. And so there are three features that I'd like to draw your attention to. So what are these three features? So yesterday we talked about something that was, so there is this question of existence, which we spent a long time talking about yesterday. Then there is the issue of avoidance, something that I'd like to talk about today. And then maybe for some other day, a story for a different day is the issue of abundance. So I'll say a little bit about what each one means. So what does existence mean? Well, if a set is large, it should contain many patterns. So the sort of moral, the principle here is if a set is large, and we talked about different notions of largeness yesterday. So if a set is large, it contains many patterns and perhaps even a pattern of my choice. Okay. And here I spoke about, as I gave as examples, um, Zemredi's theorem in the integers. This was about sets of positive density in the integers having k-term arithmetic progressions for any k larger than or equal to 3. And the second one was um, a more basic result from real analysis, Steinhaus's theorem, which says a set of positive Lebesgue measure contains an affine copy of every finite set. Okay. Now, what about avoidance? So avoidance, so it's sort of based on the principle that there can be large sets avoiding certain patterns. So there exist certain large sets, we are not saying all of them, that could avoid one or even many patterns. Okay, and I'll give you some examples in a moment. And finally, what is the abundance? The abundance is actually the flip side of the quite the opposite of this avoidance category. The principle here is that a set can be small, really, really small, and yet contain many patterns. There exist small sets that can contain so let's proceed with some examples. In the avoidance category, so if you remember how Zemredi's theorem goes, so we talked about this result yesterday, and the point of it was that suppose you have this set E, subset of the natural numbers, and its asymptotic density is positive, so E intersected with the first capital N natural numbers, has cardinality proportional to n, then that means that E contains k-term arithmetic progressions. Okay. Now let's compare this with what happens when this condition fails. And this is a sort of a quintessential avoidance statement. So this goes back to the work of Berendt and Salem and Spencer. So Salem and Spencer, and also Berendt from the 1940s and 1950s. And what they found was that there exists a subset capital E of Z mod n for n sufficiently large such that, so what does large mean? Well, clearly E sub n cannot have size proportional to n, but it's almost there. So it misses it by this much. So let's say it's capital N times. If it was a constant, then that wouldn't quite work because of Zemeredi. But this is the by how much, the factor by which it fails, which is a very small factor. This is smaller than, so this is larger than n to the power of minus epsilon for any epsilon. Okay. So, and E sub n is progression free. Okay. All right. So this is something to note that if you look at this object, this by def is bigger than or equal to n to the power of 1 minus epsilon for all positive epsilon. Okay. All right. And let's also look at the last thing that we were talking about on the last column here. So this is 1 double prime. What exactly is a small set that contains many patterns? So let's keep to this progression idea just for a little bit longer. So this goes back to an old result due to Kohakawa, Luchak, and Rodel. And they showed that random subsets of 0, 1 up to n minus 1. And these random subsets could be really of size. So let's say this random subset is capital E, and the cardinality of capital E is n to the 1 minus epsilon for some epsilon less than 1/2. These ones contain long progressions. So what do I mean by random sets? Well, there are many ways to construct them, but here is a concrete example. You could go through each integer, 0, 1 up to n minus 1, and you could flip a coin in an independent manner for each one of them, the same coin with a probability of selection being n to the power of minus epsilon. So the result that you get is this, the outcome of this experiment is this set E, and what they showed was that such random sets contain long progressions. Of course, there is the famous example, this due to Green and Tao, which is the same conclusion holds arbitrarily long progressions for primes, which is again a small set. It has density 0 and asymptotically like 1 over log n, and it contains arbitrarily long progressions. So that's an example of, these are some examples of small sets which are still rich in patterns. Okay, so let me take a quick stop to see if there are any questions so far.
There are no questions on the chat yet.
Okay. All right, so should I move on then, or do you want to? Okay, keep going.
Yeah, unless if someone has a question, please go ahead and ask.
Okay.
I think that we can go.
All right, then let's keep going then. All right. So what's the plan today? What I would like to do is, so the examples that I gave on this page over here, they're all examples in the integers. Eventually, I do want to move over to the continuum and start talking about corresponding results on the real line, say. But before I do, maybe there is a nice example, this example that we can all sort of enjoy together. I really, really like this example because it's so easy to describe and the idea is so beautiful. So I want to sort of spend a few moments trying to explain the Berendt construction and all its different ramifications. Okay, so let's look at the construction of Berendt. Um, so Berendt's example. Of a progression free. Of a large progression free set. Okay. All right, so what did he do? So the idea there was the following. So suppose let's sort of recall a few things. Do you remember that every integer has a digit expansion? So fix an integer d, a large integer, and also an n. Capital N is going to be d to the power of n, and later d is going to be chosen very large relative to n. Recall that every integer between 0 and capital N admits the digit expansion with respect to base d. So every integer x that belongs to 0, 1 up to capital N minus 1 has a digit expansion, and this digit expansion is unique. So that means that you can write x as the sum of xj d to the power of j, j from 0 to n minus 1. And these xj's are the digits, and they can take any value between xj and d. So what Berendt did, so this is sort of a nice trick where a single integer x is identified with a vector of integers x1 through xd. Okay. Now Berendt's idea was the following. So he defined, let's call this b sub n. Actually, let's call this b sub r because it's going to depend on this parameter called r. Okay. So b sub r is the set of all x's all integers x in, so this is, let's call this set um, Zn. Such that each of the digits that constitute x, they don't go all the way. They maybe stop at, let's say, d over 2 or d over 3, and you will see in a moment why. But here's the important part, that when you look at summation xj square, the sum of squares of the digits, that equals capital R. So I want us to understand this. So these are all the integers whose digits lie on a sphere of radius square root of r. So I'm going to try and draw a picture here. So this is a sphere in n-dimensional space. And somewhere here, there are these points x and y. So x is a point here. Okay. Okay. Now, here are the claims that Berendt made, and we want to sort of, let's try to enjoy this together. Um, so Berendt says, so the claim is, there are two claims. The first one is that for every R, notice that I haven't specified R yet, for every R, the set BR is progression free. Why is that? Well, let's see. Suppose there were x, y, and z in the Berendt set, which belong to a three-term arithmetic progression. So let's say x plus y was equal to 2z. And remember, if we decide to write x, y, and z in terms of their digit expansion, this would simply give you this equality. Okay. Now, here comes the part where this bound on the xj's is important. If each xj and yj is less than d over 3, the sum is less than 2d over 3 on either side, and these are, of course, integers. And this comes down then, boils down to having two integers that are equal, and their coefficients here are less than d, and the digit expansion is unique, which means that digit for digit, they must match up. In other words, xj plus yj has to be equal to twice zj for every j. Oh, 0 to n minus 1. Okay. So here's x, there is some point y also in the same set. But now you see why this idea of Berendt was so brilliant, because he chose his points on a sphere. And x, y, and z are supposed to be 3 points on a line and all lying on the sphere. And you can see why that can't happen, because a sphere is strictly convex. So this implies that the vector x plus the vector y is equal to the vector 2z. And because they lie on the sphere, the only way this is possible is for these 3 points to be identical, which means, of course, that as integers, x, y, and z have to be the same. So there is no non-trivial three-term arithmetic progression in a Behrens set. Okay, now comes the part where this is progression free, but is it large? Now let's tackle that one. Well, right now there are many possible choices of capital R, and regardless of which one you pick, this is progression free. I claim that, so this is part two of the claim. So part two of the claim is that there exists an R such that the cardinality of BR is large. And I want to explain why and what exactly does large mean. So we'll see. So notice that just by virtue of the definitions, these are all disjoint sets. So these are disjoint in R. Okay. And how many possible choices of BR can there be? Let's write that down. So the number of choices of capital R is at most, well, let's see. Each xj can take the value from 0 to d over 3. So the total number of possible choices of capital R is n times d over 3 to the power of 2. Okay, so these are all the possible choices of R that one can get. Okay, now as we run through all the values of R, we must exhaust all the possible choices in Z mod n whose digits go up to d over 3. So let's make that statement next. So if we sum over all these capital R's from 0 to n times d over 3 square, what do we get? We get all the x's in Z mod n whose digits go up to d over 3. Okay, and this we can count. This is exactly d over 3 raised to the power of n. Now comes the pigeonhole principle. So the pigeonhole principle says that, well, if the sum of all these cardinalities adds up to this much, there must be one R for which the cardinality is d over 3 to the power of n divided by the total number of the total number of summands, and the total number of summands is n times d over 3 square. So this is a large set. This is 1 over n d over 3 to the power of n minus 2. And this is large, and this is actually exactly the claimed bound. So I'll let you check that this is larger than capital N times e to the power of minus constant times square root of log n. So if this is your capital N and d is large. Okay, so I crammed a lot of things in here. So I'm going to stop and see if you have a question about Behrens construction, because I'm going to take this and try to do some stuff with it in my next page.
There are no questions in the chat, but if someone has a question, please go ahead.
Just an observation, maybe.
Yes.
We avoided one pattern by really submitting to another pattern, which is being on these spheres, right?
That's right. So
Okay.
that's a great observation. Is that you, Christian?
Yes, Christian. Thank you.
Okay, all right. I can't see you because of the screen in front of me.
Yeah.
Hi. And
Hi.
yes, that's exactly the thing. Because it's a large set, just by virtue of being large, it has to accommodate certain patterns. As you mentioned here,
Right.
their digits are all required to lie on a sphere, and that itself is a pattern of its own. We avoided one set of patterns and landed into another. And this is going to be this recurring theme. I'm so glad you brought this up, because I'm hoping to get to the point where we say that if you have a favorite pattern, I can maybe find sets, large sets that avoids your favorite pattern, but you can't avoid a whole
All
bunch
five.
of them.
That's
Right. Okay.
There's another question. It says,
There
how
is another question.
exactly?
Yeah, there is another question in the chat. How exactly was pigeonhole used?
Oh, how exactly was pigeonhole used? So let's see. I'm going to maybe get myself a fresh page so that you can see. So were we okay with this identity that when we look at the cardinality of the Behrend set, and R goes all the way from 0 to n times d over 3 to the square, this is equal to d over 3 to the power of n. Were you asking about this identity, or are you okay with that?
Joshua, can you answer that?
That's the part I was confused about.
Okay, so you are asking why is this true? So
Mhm.
remember, BR was the set of all x's such that a 0 was less than or equal to xj less than d over 3, and summation xj squared was r, right?
Yeah.
Okay, so what I was saying was, whatever choice of take any x in Z mod n with this property, okay? Then summation xj squared has to be something, some capital R, which is in my collection.
Right.
So when you take the union over all possible capital R's, you have basically everything in this set.
And you're using your statement from earlier that R is disjoint, or the set is disjoint over the R's.
And they absolutely, because they live on spheres of different radii.
Right. Okay.
And therefore, this is the size of this set.
Got it. Okay. Let's make sure I was following that. Thank you.
Okay, all right. And then the pigeonhole says that there has to exist an R for which this one of them has to be large. Okay. All right then. So that's great. So now let's go over to the continuum and ask the question: how can we use the Behrend set to? So can we use the Behrend set to obtain a large progression-free set in the real line? And there are many examples of a large progression-free sets in the real line using many different constructions. The reason I want to use the Behrend set is because it exemplifies this method where if you have an avoiding set in the discrete regime, how you can transfer it to obtain an avoiding set in the continuous regime. So it's sort of a prototype for that kind of transference. All right. So the answer is yes. And here's how the construction proceeds. So we do this via a Cantor type construction. So if you have seen a construction of a Cantor middle third set in your real analysis course, then you will notice certain similarities here. Okay. All right. So what do we do? So it's an iterative construction. You start with E0, and E0 is the interval 0, 1. All right. Next, we go to E1. And what do we do with E1? Well, here's a picture. This is 0, 1. At the first stage, we introduce a copy of the Behrend set inside this. So let's say this, we are going to call this the union over ij, or let's call it ij1. What is j1? Well, j is a Berent set, belongs to a Berent set B. Let's call this B star 1. And what is B star 1? This is contained inside Z mod N1. And these are points J1 over N1. So let me draw these little intervals here. So this is an interval. The length of this interval is 1 over N1. Same over here. So this is my E1. Okay. All right. And what is I sub J1? These are the intervals. So I sub J1 is by definition the interval J1 over 1 and 1 with this little fudge factor of 0 to 1 over N1 attached to it. Okay. So now obviously it's not true that E1 itself is a progression-free set. That's too much to expect because it consists of small intervals, and the moment there are intervals, intervals contain plenty of progressions, as we all know. But it does avoid progressions in a different sense, in a sort of a weak sense, in the following way. So note that the only way E1 can contain progressions is if there exist XYZ in E1 in progression such that X plus Y is equal to Z, then there must exist some basic interval J1 such that X, Y, and Z all lie in that single basic interval I sub J1. Okay, so you cannot have X here, Y there, and Z there and hope to meet a progression. Your X, Y, and Z all have to be clustered over here. So we haven't fully avoided progressions, but we have narrowed down their common difference to one single interval. And now you see how this is going to go. What we are going to keep on doing is simply, so E2, we are simply going to iterate this construction. So in the next round, we will have E2 to be the union of I, J1, J2. So J1 would belong to B1 star, and J2 would belong to B2 star. And let me write out what I mean by this. This is going to be J1 over N1 plus J2 over N1 N2 with a tiny interval of length 1 over N1 N2 attached to it, to this left-hand endpoint. And J1 belongs to a Berent set, and J2 belongs to a Berent set too. Okay, so what have we done? In this picture, so I'll just magnify this picture over here. So we had this interval, let's say J1 over N1 and J1 plus 1 over N1 from the first step. At the second step, all we have done is to break this up into n too many equal pieces. So each length is 1 over N1 N2. And we have picked out a Berent set from those ones. Okay, and once again, if X, Y, and Z were already in this interval to begin with, after you run this construction, if X, Y, Z belong to E2, then the exact same computation is going to show that this time X, Y, and Z would be constrained to lie within an even smaller interval, I, J1, J2. And now you can see how this is going to proceed as you keep going. The diameter of the set X, Y, Z is going to shrink, keep on shrinking, and eventually become 0. So in the limit, your E is the intersection of En, and this is going to be progression free. I think there was a question, right?
Yes. Do you assume n sub 2 larger than n sub 1?
No,
Much larger
right
than n sub
now,
1?
I don't. So we can choose N1 to be less than or in fact, you can choose all of them to be equal to each other if you like. Okay.
Any
All
other
right.
questions?
Any other questions?
The Berens sets can be all the same? Or
The Berens,
can-
if let's say we are in the situation where capital N1 equals capital N2 equals et cetera, equals capital N, then
Yeah.
yes,
Okay.
all the Berens sets could be the same.
Okay.
Okay. All right. So let me see. So this is certainly a progression-free set. Is it a large set? So we talked about being, is it large? Well, this set capital E is large because the building block, the Berens set is large because B star is large. And I'll sort of show you, try to prove this to you in the simplest case with the Minkowski dimension. So if you remember how, so each E sub n, so how do you note this? So note that if you look at the nth iterate of this construction, En is the disjoint union of how many intervals? Well, it's the product of the cardinality of Bj, the cardinality of the Berens set, these many intervals of length 1 over n1, n2, n sub n. So the Minkowski dimension is the easiest to compute, so I'll do that. So the Minkowski dimension of E is equal to the log of this product of the cardinalities divided by the log of n1, n2, n sub n as capital N, as little n goes to infinity. But remember, the Berens set was almost like n1, n2, nn with some fudge factor, which doesn't really make a difference to this limit. So this limit is 1. So when we say large, and in fact, a little revamping of this calculation will also give you Hausdorff dimension. So when I say large, what I really mean is the Hausdorff dimension of this progression-free set is actually full. It's 1. Okay. Any other questions?
Nothing in the chat, but if anyone has a question, please go ahead.
Okay. All right. So what I do want to now talk about is something that Christian actually observed already. So I want to place this construction. What have we just now done? We have found, okay, let's go back just for a second. And what we have found is a full dimensional progression-free set, full Hausdorff dimension using the Berens construction. Now, what has been done, it's fairly recent, well, it sort of dates back to about 2014 or 2017, I forget. But what is known is that by tweaking this result a little bit, one can not only get a full Hausdorff dimensional set that is progression free, one can actually get Fourier dimension as well. So in fact, I want to tell you, so these kinds of Fourier um, avoiding sets with large Fourier dimension, they often rest on random constructions, and tweaking of the Behrens set gives you that. So let me say how you can upgrade this construction to get a progression-free set of Fourier dimension 1. So this is actually due to Pablo Schmerken. So he also used the Behrens construction as his building block. And what he did was, at every stage, instead of simply inserting the Behrens set just by itself, he introduced a random shift. So okay, what does that mean? That means, what are these LJ1s? The L sub J1, these are independent and identically distributed random variables that are uniform on Z mod N1, which means that you inserted your Behrens set. This is the set that you inserted. That's all good. And then you you put in a shift. So you now shift this set to the right by a certain amount, so that maybe this moves to this part, this moves to that part, and this whole set moves and wraps around. And the amount you shifted by, that is L sub J1. And then he uses probabilistic sort of concentration inequalities to show that not only is this resulting set of large Hausdorff dimension, it's of large Fourier dimension as well. And this shift is important. It makes no difference to the avoidance criteria, because this equation x plus y equal to 2z is shift invariant. So shifting doesn't make a difference to the avoidance of this set. Okay. So let's sort of take a look then at what's our conclusion, our summary so far. So summary. There exists a set of Fourier dimension and Hausdorff dimension 1, which is progression free. And this is there is an earlier work of math.k and with extensions by Alexia Yavikole, which show, and this is a very strong result, which says that there exists a set E of full Hausdorff dimension which is rationally independent, meaning it avoids all rational relations. So what does rationally independent mean? That if there is a relation like this, summation alpha j xj, a linear dependence relation equal to 0, where the xj's are from the set E and the alpha j's are rational, and for any p larger than or equal to 2, then the only way this is possible is if all the alpha j's are equal to 0. Okay, so it seems like avoiding, you can have very, very large sets, about as large as it gets. This is, by the way, of course, goes without saying, the Lebesgue measure of this set is 0, even though it's a full dimension. It can avoid all rational linear patterns, and in fact, therefore, it can avoid progressions, which is a very special kind of rational linear pattern. So, what exactly is then the point of looking at so many different notions of dimension like Hausdorff and Fourier and Minkowski if there are always going to be large sets that keep avoiding patterns? So that brings me to this end of this. So the last comment that I want to make today is that it is possible to get large Hausdorff dimensional sets which avoid lots and lots of patterns. The claim is that you cannot get large Fourier dimensional sets that avoid tons of patterns. And this goes back to this comment that Christian made, that in the process of excluding one, you have included many others. And the notion of Fourier dimension makes that precise. So I'm going to share with you a very short computation to sort of make my case. Okay, so here's my claim. That there exists, no, I'm sorry. Let E be any subset of 0, 1, whose Fourier dimension, and this is just a prototype result. There are many generalizations, but I'm not going to go for the most strong statement right now. The Fourier dimension is large, let's say larger than 2/3. Then E must contain a non-trivial solution of some equation of the following form. A plus B Z equals AX plus BY, where X, Y, Z, these have to be points in E, and A and B are natural numbers. Okay, so I wrote this statement out in the simplest possible way, and I want to convince you why you should believe this, okay? And we are going to go for a proof by contradiction. So we are going to assume that E doesn't contain any such pattern, any non-trivial solution of an equation like this. But of course, its dimension is large, which means that E supports a probability measure with good Fourier decay. So E supports some measure mu such that mu hat of xi is less than 1 plus mod xi to the power of negative beta over 2. Okay, so now what do we do with this? We do this rather simple computation. So we are going to look at d mu x. This is a probability measure, and we take 3 copies of it. So of course it's 1. And then we spread it out into 3 separate integrals, d mu x, d mu y, and d mu z. Okay, so I haven't done anything so far. Now, what do we do? This is a symmetric expression in XYZ. So what I'm going to do is I'm going to say that by symmetry, I can simply break this up into 6 pieces and they're all equal. So I restrict this domain of integration to x
Here is
less.
a question, what is beta?
Oh, remember? So I wish I could. So if we have the Fourier dimension was supposed to be the supremum over all exponents beta in 0 to 1, such that mu hat of xi is, so this is the, by definition, the Fourier dimension of a set. So this beta is some exponent larger than 2/3. So if that helps. Does
I
that
see,
make?
David, you asked a question. Does that clarify
So
your question?
let me write down the definition of the Fourier dimension, maybe just to be on the safe side. The Fourier dimension of a set E is by definition, it is the supremum over all exponents beta, such that E supports a probability measure mu with the property that mu hat of xi decays like mod xi to the power of negative beta over 2 at infinity for all xi. So this was the definition, and that's what I was using here.
I think that the question has been clarified. Thank you, Malabika.
Okay. All right, so let's just wrap up in these last 2 minutes. So we have this, and all we are going to do now is make a change of variable. So what's the change of variable? I'm going to simply put z to be tx plus 1 minus ty. Because z is in between x and y, we can always find such a t, and we make a change of variable, which would have d mu x, d mu y, and one has to justify this change of variable, of course, but you can sort of see how we are going to do this. We sort of put this in. And there is a Jacobian factor, which will be x minus y. But yesterday, I told you about this multilinear form which measures the existence of configurations. So this is a multilinear form um, which is, I'm sorry, this should be a y, shouldn't it? Okay. So this is an integral. I want to write it in 2 parts. There is an integral outside t from 0 to 1, and inside there is a double integral in x and y, which shows up. And this is what I was talking to you yesterday about, the lambda t of the function f, where f is the function x minus y. And this is non-zero. Um, if it is non-zero, it shows that the support of mu contains this pattern x, y, tx plus 1 minus ty. I am claiming that this is 0. The right-hand side is going to be 0. This object, 0. Why is this 0? It is 0 because of this assumption that I made, namely that E doesn't contain a non-trivial solution of any equation like this with rational coefficients, which means that the function t going to lambda t is 0 on all rational points on Q intersected with 0, 1. And this is a continuous function. So if you now you know this from real analysis, if you have a continuous function that is 0 on the rationals, it has to be 0 everywhere. And if it is 0 everywhere, this integrand vanishes, and we have shown that 1 is less than 0, and that's of course a contradiction. Okay, so I think the moral of this story is that the Fourier dimension, the finest notion of the dimension we discussed in these two talks, somehow manages to identify the existence, somehow a set with large Fourier dimension manages to signal a richness of rational linear patterns. There are many results that generalize this philosophy now. I should also have mentioned that this last claim is joint work with Yu Liang and myself. And with that, I'll stop and wait for your questions.